All right, welcome back. So theorem 2.16, we're not going to do a proof of it here. There's a proof in the textbook if you want, but really to see why this works, I think you just need to see examples like we just did to see how the columns of the elementary matrix, when you multiply that on the right, are doing a similar linear combination of the columns of the matrix A on the left. And that results in that column operation being done to A. Now, by the way, these footnotes that are showing up all over the place, I really tried hard to get them to show up in the right place. That's from down here. But despite my efforts, they're still all over the place. So sorry about that. Anyways, let's look at theorem 2.17 that's similar to 2.16. This one says elementary matrices do row operations. And same idea, but this time E is an elementary matrix that's the result of doing some row operation to the identity. Then EA multiplied the other way around with the elementary matrix on the left now is the result of doing the same row operation to A. To prove this, we're going to start by noticing a few things. One is that rows of E are equal to the columns of E transpose. And same thing with A. And because of this thing with E and E transpose, we can say whatever row operation turns the rows of the identity matrix into E, that's basically the same thing as the column operation that turns I transpose, which is the same thing as I, into E transpose. It's really the same operation. Let's look at an example of that. Let's say that E represents a multidata placement row operation. So for example, replacing row 1 with the sum of 4 times row 3 plus row 1. If we do that same thing to the columns of the identity matrix, but just with the columns instead, so 4 times column 3 plus column 1 to replace column 1. So literally just replacing rows with columns. So here's the identity matrix, but we're just going to do the same operation here. So we're doing 4 times this column, adding that to the first column. That's going to make this be a 4 here. And that means these are transposes of each other. The same thing that we did to row 3, we just did that to column 3 of the identity. So it is the same operation. So that also means that A transpose times E transpose using theorem 2.16, because we're multiplying A transpose by an elementary matrix on the right now, is the same thing as doing that column operation to the columns of A transpose, also known as rows of A. Now, the trick is that E times A is the transpose of this, A transpose, E transpose, because the transpose of the transpose is itself. Just when you have a product of these, it comes out in backwards order. That gives you the result. We're turning these columns that have been transformed using that column operation, we're turning them back into rows. Okay, So now that proof, I don't know, might feel a little abstract. Like using these properties here might not be very like satisfying. You might not really see what's going on here. And this is an example of why math can be powerful. Like it might be possible to use the facts that you know about matrix multiplication, for example, to prove things about matrix multiplication that you don't really have an intuitive understanding of. You don't have like concrete examples. So it also helps to do some concrete examples. So let's do an example of this here. We have the same E and F as before in the previous example, but this time we are multiplying it the other way around. We're doing the E and F on the left. Okay, so let's just multiply E times A and we'll see how this works. Now first, I'm just going to write this out using the row column rule. So for example, row 1, column 1 is just going to be 1A plus 0D plus 0G, like so. And then let's go to the next column here. This is going to be 1B plus 0E plus 0H, which is, of course, just going to come out to be 1B. So it's not changing that. And here we're doing 1C plus 0F plus 0I. And let's just continue that for the rest of this matrix. And at this point, before we actually work it out, like simplify it, because I know we could simplify this right now, what I want to point out is that what this says, each row of EA is a linear combination of the rows of A using the entries from the corresponding matrix on the left as weights. So what do we mean by that? This row here you could write as the sum of 3 different rows. I could write this as 1 times the row ADG plus 0 times the row DEF plus 0 times the row GHI, right? So like this 1 comes from here, here, and here. This 0 comes from here, here, and here. And this 0 comes from here, here, and here. And likewise, we could do the same thing with the second row and the third row. Like so. So, yeah, this works out a similar way. I think maybe the important points are where the ones are, where like things changed. So if you do a swap to rows 2 and 3 of E, that's this one, which ended up here, and this other one that ended up here. And that means the result of EA is, well, 1 times the first row, ADG, for the first row. And then the second row is 1 times the third row of A. That's the GH. Oh, this should be A. Jesus Christ. Whoops, that should be A, B, C here. Good if you caught that mistake. All right, it looks like that worked. So doing that linear combination using these different rows essentially swapped rows 2 and 3 of the result. All right, let's just check the same thing happens with F. First, just using the regular row column rule. So yeah, that's what I get using the row column rule. And for the first row of this one, I can think of this whole row as a linear combination of 3 different rows. 1 times ABC plus -7 times D, E, F plus 0 times G, H, I. And it's the same idea for the other rows. We're just using different things as a linear combination. Like here we have 0 always gets multiplied by that first one, and then 1 is always being multiplied by the second row of A, and then the 0 is always getting multiplied by the third row. So that's another way you can see this is 0, 1, 0 here. And the last one's going to be 0, 0, 1. Anyways, what you get is A minus 7D, B minus 7E, and C minus 7F. And then the other rows are unchanged. And so yeah, because, as we're trying to show here, the result of FA is a linear combination of the rows of A using the corresponding entries in that row of F as weights, we're doing the same row operation to A that was done from the identity to get F. All right. Yeah, we can see now that you can think of elementary matrices 2 ways. If you want to think of it as doing a column operation, you multiply it on the right. If you want to think of it as a row operation, you multiply it on the left. And this is going to allow us to apply things we know about row operations like pivot positions and all that stuff to write it in the form of matrix multiplication. And that's going to help us prove the invertible matrix theorem in the next video.